Welcome! In this video, we'll be diving into LeetCode problem number 1061, titled Lexicographically Smallest Equivalent String. This problem challenges us to use equivalence relationships between characters to transform strings in a lexicographically smallest way. We'll explore the problem requirements, step through the solution, and discuss the algorithmic concepts involved. Let's get started. In this problem, we are given three strings, s1, s2, and base str. The strings s1 and s2 have the same length, and they define equivalence relationships between their corresponding characters. For example, if s1, I, is mapped to s2, I, then those two characters are considered equivalent. This equivalence is transitive, meaning if one character is equivalent to another, and that second character is equivalent to a third, then the first and third characters are also considered equivalent. The goal of this problem is to use these equivalence relationships to transform base str into its lexicographically smallest equivalent string. To achieve this, we replace each character in base str with the smallest character in its equivalence group. The output is the transformed version of base str that satisfies this condition. To better understand the problem, let's look at the first example. Here, we have s1 as Parker, s2 as Morris, and base str as parser. From s1 and s2, we can derive equivalence mappings. P is equivalent to M, A to O, R to R, K to I, and E to S. By combining these mappings through their transitive relationships, we form equivalence groups P, M, A, O, R, K, I, and E, S. Now, to transform base str, we replace each character with the smallest character from its equivalence group. For instance, P is replaced by M, the smallest in P, M, while it remains A as it's the smallest in A, O. Similarly, R stays as R. This process continues for all characters in base str. Continuing with the first example, we replace S in base str with E, the smallest character in the equivalence group, E, S. The next character, E, remains unchanged because it is already the smallest in its group. Finally, the character R is replaced with itself, as it is the only member of its group, R. After processing all characters in base str, the resulting string is makek, which is the lexicographically smallest equivalent string. Now let's look at another example. Here, s1 is hello, s2 is world, and base str is hold. The equivalence relationships from s1 and s2 give us mappings, h to w, e to o, l to r, and o to d. Using transitive relationships, we group these mappings into H, W, E, O, D, and L, R. For the second example, we transform base str by replacing each character with the smallest in its equivalence group. The first character, H, is replaced by H, as it's already the smallest in H, W. Next, O is replaced by D, the smallest in E, O, D. The character L remains unchanged since it is the smallest in L, R. Finally, D also remains unchanged because it's already the smallest in E, O, D. After processing all the characters, the result for this example is HDLD. Let's consider one more example to reinforce the concept. This time, S1 is ABC, S2 is XYZ, and base str is CBA. The equivalence relationships from S1 and S2 give us mappings, A to X, B to Y, and C to Z. In the third example, the equivalence mappings form disjoint groups, A, X, B, Y, and C, Z. To transform base str, we replace each character with the smallest in its equivalence group. The first character, C, is replaced by Z, the smallest in C, Z. Next, B is replaced by Y, the smallest in B, Y. Finally, A is replaced by X, the smallest in A, X. The resulting string is ZYX. Now let's discuss the constraints and edge cases. The input strings have lengths between 1 and 1000, and S1 and S2 are guaranteed to have the same length. All characters are lowercase English letters. Some interesting edge cases include situations where there are no equivalence mappings, single character base str, or all characters being equivalent. Understanding these cases will help ensure a robust solution. To solve the problem of finding the lexicographically smallest equivalent string, we need to evaluate the equivalence relationships between characters in the given strings S1 and S2. Our goal is to transform base str using these relationships to produce the smallest possible string in lexicographical order. One approach is a brute force method, where we directly replace characters in base str based on the mappings derived from S1 and S2. Specifically, we map each character in S1 to its corresponding character in S2 and vice versa, and then iteratively replace characters in base str with the smallest equivalent character in the mappings. However, this approach has significant drawbacks. It is computationally expensive, as repeated replacements lead to a time complexity of O(n squared), and it struggles to handle transitive equivalence effectively. To address these inefficiencies, we turn to the optimized union find approach, which treats the problem as a graph of connected components. This strategy allows us to group equivalent characters and determine their smallest lexicographical representative efficiently. The union find approach begins by initializing a union find structure to represent all the characters from A to Z. Using this structure, we can efficiently group characters into equivalence classes. For each pair of characters, S1, I, S2, I, provided in the input, we perform a union operation, effectively connecting their respective components. Once this setup is complete, we proceed to transform base str. For each character in base str, we use the union find structure to determine the root of its equivalence class, which represents the smallest character in that class. By replacing each character with its smallest equivalent, we construct the desired output string. The efficiency of this approach is a key advantage. With a time complexity of O(n asterisk alpha n), where alpha n is the inverse Ackermann function that grows extremely slowly, the algorithm is nearly linear in practice. Additionally, the space complexity is minimal, requiring only O(26) to store the union find structure for all lowercase letters. This approach not only handles transitive equivalence seamlessly but also avoids redundant operations, making it far more efficient than the brute force method. The union find approach is the most suitable solution for this problem due to its balance of efficiency and correctness. At its core, the problem can be visualized as a graph where characters are nodes and equivalence relationships between them are edges. Union find excels at managing such connected components. By always attaching the smaller character as the parent during union operations, we ensure that each equivalence class is represented by its smallest lexicographical character. This guarantees that the transformed string is optimized. Furthermore, this method avoids the repeated transformations and checks inherent in the brute force approach, making it far more scalable for larger inputs. While other graph-based methods, such as BFS or DFS, could also solve the problem, they involve higher traversal costs and are less efficient for this specific use case. In conclusion, union find stands out as the optimal strategy, providing a robust and scalable solution to the problem of transforming base str into the lexicographically smallest equivalent string. In this problem, we're tasked with finding the lexicographically smallest equivalent string given two input strings, S1 and S2, which define equivalence relationships between characters. These relationships mean that if a character in S1 corresponds to a character in S2, they are considered equivalent, and this equivalence can extend transitively. Using this equivalence, we need to transform another string, base str, so that it adheres to the smallest lexicographical order among all possible transformations. To solve this, we can model the equivalence relationships as an undirected graph, where each character is a node, and equivalences form edges between nodes. The key is to use a union find data structure to group equivalent characters efficiently. Each group will have a leader, which is the smallest character in lexicographical order, and this leader will represent the group during the transformation process. Now, let's look at how union find is implemented for this problem. First, we initialize the data structure with a parent array, where each character initially points to itself as its own parent. This ensures that every character starts out in its own group. Then, the find operation is implemented with path compression, which makes the structure efficient by ensuring that all nodes in a connected component point directly to their group's leader. For the union operation, we always attach the group with the larger leader to the group with the smaller leader. This ensures that the smallest character in lexicographical order becomes the leader of the group. Once the union find structure is ready, we build equivalence classes by iterating through the characters in S1 and S2. For each pair of characters, we perform a union operation to group them together. Finally, for the transformation step, we process each character in base str, finding its leader and replacing it with the smallest character in its equivalence group. The result is the transformed string, which we then output. There are several key insights that make this approach efficient and robust. First, union find is particularly well suited for problems involving dynamic equivalence relations. The use of path compression and union by rank ensures that operations are nearly constant time. By attaching larger leaders to smaller leaders during union operations, we guarantee that the group leader is always the smallest character, which simplifies the transformation process. There are also important edge cases to consider. For example, S1 and S2 might represent completely disjoint sets of characters, meaning no equivalence exists between their groups. If base str contains characters not present in S1 or S2, those characters remain unchanged in the output. Additionally, if S1 and S2 map a character to itself, this has no effect on the equivalence relationships. The main data structures used are the parent array, which tracks the leader of each group, and optionally a rank array to optimize union operations. In terms of complexity, the algorithm is highly efficient. Union find operations run in nearly constant time, and processing all characters in S1, S2, and base str is linear with respect to their length. To break down the complexity further, union find operations like find and union are practically constant time, denoted as O, alpha, n, where alpha is the inverse Ackermann function, which grows extremely slowly. Processing all characters in S1, S2, and base str takes linear time, O, n, since we iterate through each character exactly once. Combining these, the overall time complexity of the algorithm is O, n. For space complexity, we use an array of fixed size 26 for the lowercase English letters, making the space requirement O1. Now, let's explore the pseudocode to see how the algorithm is implemented. First, we initialize the parent array so that each character is its own parent. Then, the find function is defined with path compression to ensure efficiency, and the union function ensures that the smaller leader always becomes the parent of the larger leader. This is how we maintain lexicographical order within the equivalence groups. After defining these operations, we iterate through S1 and S2 to perform union operations and build the equivalence classes. As we continue the pseudocode, for each pair of characters in S1 and S2, we call the union function to group them together. Once all equivalences have been processed, we move on to transforming base str. For each character in base str, we find its leader using the find function, then replace it with the corresponding smallest character in its equivalence group. This ensures that the transformed string respects the lexicographical order among all possible transformations. Finally, we join the characters to form the output string and return it. Let's look at an example to clarify the process. Suppose S1 is ABC, S2 is BCD, and base str is XYZ. The equivalences are A left-right arrow B left-right arrow C left-right arrow D, forming a single group. Using union find, we determine that it is the smallest leader of this group. When transforming base str, each character is replaced by its corresponding leader, resulting in the transformed string. The final output of the example is the transformed string, which respects the lexicographical order of the equivalence groups. Key operations in the implementation include the union operation, which ensures that characters are grouped together based on their equivalence relationships, and the find operation, which uses path compression to efficiently retrieve the leader of any group. Additionally, the use of lexicographical ordering ensures that the leader of each group is always the smallest character, simplifying the transformation step. By combining these operations with the properties of union find, the algorithm efficiently solves the problem while handling edge cases and maintaining optimal performance. This concludes the explanation of the algorithm and its implementation. This implementation solves LeetCode problem number 1061, lexicographically smallest equivalence string, by constructing equivalence classes among characters using the union find, disjoint set, data structure. First, we define two helper functions, find and union. The find function retrieves the root parent of a given character while performing path compression, ensuring that every character directly points to its root for efficiency. The union function merges two equivalence classes by attaching the smaller root to the larger one to maintain lexicographical order. The parent dictionary initializes every character, A to Z, as its own parent. This represents that initially, each character is in its own equivalence class. Next, we iterate through pairs of characters from S1 and S2, calling the union function to merge their equivalence classes. This step builds the relationships between characters provided in the input strings. Finally, we transform the base str string by replacing each character with its smallest lexicographical equivalent, determined using the find function. Each character's root parent is found, and the results are joined together to produce the final output. This approach ensures correctness and efficiency. The union find operations are nearly constant time due to path compression, making the overall time complexity O, n plus m, where n is the length of S1/S2 and m is the length of base str. The code handles edge cases such as when characters in base str have no mappings explicitly. This solution is concise, efficient, and adheres to the problem's requirements. Here, we begin by defining our Java class and implementing the smallest equivalent string method. First, we create a hash map called parent to store the root parent of each character. We initialize this map so that each character from A to Z is its own parent. This setup allows us to treat each character as its own equivalence class initially. Next, we define a helper method called find which uses path compression to efficiently determine the root parent of a given character. The path compression step ensures that during repeated lookups, the parent pointers are updated directly to the root, optimizing future queries. Additionally, we define a union method that merges two equivalence classes by connecting their root parents. To maintain lexicographical order, we ensure that the smaller character becomes the parent of the larger one whenever two classes are merged. After defining the helper methods, we proceed to build the equivalence classes by iterating through the strings S1 and S2. For each pair of corresponding characters, we call the union method to group them into the same equivalence class. Once all the equivalence classes are formed, we construct the lexicographically smallest equivalent string. To do this, we iterate over each character in the base str string, find its root parent using the find method, and append the root character to a string builder. This ensures that each character in the resulting string corresponds to the smallest equivalent character in its equivalence class. Finally, we return the constructed string by converting the string builder to a string. To solve this problem, let's start with the first example where S1 equals ABC, S2 equals BCD, and base str equals ABCD. The goal is to find the lexicographically smallest equivalent string for base str. First, we initialize a parent dictionary where each character is its own parent. This means every character from A to Z starts in its own equivalence class. Next, we process the character pairs from S1 and S2 to build equivalence classes. For the pair A, B, we find that the parents of A and B are themselves, and since it is lexicographically smaller than B, we make A the parent of B. At this point, the parent dictionary updates so that B points to A, while all other characters remain unchanged. We continue processing the pairs to further refine the equivalence classes. For B, C, the parent of B is now A, and the parent of C is C. Comparing A and C, A is smaller, so we set C to have A as its parent. Similarly, for C, D, the parent of C is now A, and the parent of D is D. Again, A is smaller than D, so we set D to have A as its parent. At the end of this process, all characters in the range A to D share the same parent, A. Now, to transform base str, we replace each character with the smallest equivalent character by finding its parent. For A, B, C, and D, their parent is A. This gives us the transformed string AAAA as the output. In the second example, we consider disjoint sets where S1 equals PQ, S2 equals RS, and base str equals PRQS. Just as before, we start with each character being its own parent. Then, we process the pairs to form equivalence classes. For P, R, the parent of P is P, and the parent of R is R. Since P is smaller, we make it the parent of R. Next, for Q, S, the parent of Q is Q, and the parent of S is S. Here, Q is smaller, so we make it the parent of S. At this point, we have two disjoint equivalence classes, one where P is the parent of R, and another where Q is the parent of S. To transform base str, we determine the smallest equivalent character for each letter. For P, its parent is P, and for R, its parent is also P. Similarly, for Q, its parent is Q, and for S, its parent is also Q. Replacing each character in base str with its smallest equivalent gives us the result PPQQ. This example demonstrates how the solution handles disjoint sets of equivalence classes, ensuring that transformations respect these independent groups. Next, we look at a case where all characters are already equivalent. In the final example, we have S1 equals ABC, S2 equals ABC, and base str equals cab. Here, the characters in S1 and S2 are already paired with themselves, meaning no changes are needed to the equivalence classes. Starting with each character as its own parent, we process the pairs A, B, B, and C, C. Since each character is already its own parent, the parent dictionary remains unchanged. Transforming base str equals cab involves finding the parent of each character. For C, A, and B, their parents are C, A, and B, respectively. This means the transformed string is the same as the original, cab. This case illustrates that the solution preserves the structure of already equivalent strings without unnecessary modifications. To analyze the time complexity of this solution, we begin with the initialization of the parent dictionary. Here, we map each character from A to Z to itself. Since there are only 26 lowercase English letters, this step requires iterating through all of them and is completed in O(26) time, which simplifies to O(1), because the number of characters is constant. Next, we look at the union operations used to build the equivalence classes. For each pair of characters in S1 and S2, we call the union function, which internally performs two find operations. Using path compression, the amortized time complexity of find is O, alpha, V, where alpha is the inverse Ackermann function, and V is the number of nodes, which is 26 in this case. Since this is constant for our problem, each union operation runs in effectively O(1) time. With n pairs of characters in total, the combined time complexity for all union operations is O(n). Now, we consider the transformation of base str. For each character in base str, whose length is m, the find function is called to determine its root in the equivalence class. As before, each find operation has an amortized time complexity of O(1) due to path compression. Thus, transforming all characters in base str takes O(m) time. Adding everything together, the overall time complexity of the solution is O(1) for initializing the parent dictionary, O(n) for the union operations, and O(m) for transforming base str. This gives us a total time complexity of O(n) plus m, where n is the length of S1 and S2, and m is the length of base str. Next, we analyze the space complexity. Starting with the parent dictionary, it stores 26 key-value pairs, where each key is a character from A to Z, and each value is its parent character. This requires O(26) space, which simplifies to O(1), because the number of characters is constant. Additionally, the find function uses recursion for path compression. In the worst case, the depth of recursion can be OV, where V is the number of nodes, which is 26. Since this is constant, the space used by the recursive stack is O(1). Finally, the input strings S1, S2, and base str together take O(n plus n plus m) equals O(n plus m) space. Combining all components, the total space complexity is O(1) for the parent dictionary and stack, plus O(n plus m) for the input strings. This results in an overall space complexity of O(n plus m). Let's compare this optimized approach with a naive approach. A brute force solution would involve repeatedly scanning through S1 and S2 to identify and merge equivalent characters. This process would take O(n squared) time to build equivalence classes and another O(m) time to transform base str, resulting in a total time complexity of O(n squared plus m). The space complexity for the naive approach is O(n plus m), accounting for the input strings. In contrast, our optimized approach leverages the union find data structure with path compression, reducing the time complexity to O(n plus m). The space complexity remains O(n plus m), but the significant improvement in time complexity makes this approach far more efficient. The mathematical justification lies in the union find's amortized cost of O, alpha, V, for find and union operations. Since alpha, V, grows extremely slowly and is effectively constant for practical inputs, the overall time complexity is dominated by the linear traversal of the input strings, confirming that it is indeed O(n plus m). Let's start by addressing some common mistakes you might encounter when solving this problem. First, it's crucial to handle all connected components in the equivalence graph properly. For example, if A is equivalent to B and B is equivalent to C, then A, B, and C must all be treated as a single group. Failing to account for these transitive relationships can result in incorrect transformations of the base string. Next, pay attention to your union find implementation. Errors like skipping path compression or not using union by rank can severely impact the efficiency of your solution. Without these optimizations, the algorithm can degrade to quadratic time complexity for larger inputs. Another issue to watch out for is excessive use of string operations. For instance, repeatedly concatenating strings inside a loop is costly. Instead, build your result using a list and join it at the end for better performance. Additionally, when merging two equivalence classes, always ensure the smallest character becomes the representative. This guarantees the output remains in lexicographical order. Lastly, don't overlook edge cases. Scenarios like empty strings, identical S1 and S2, or base str containing characters not present in S1 or S2 can lead to runtime errors or incorrect outputs if not handled properly. Now, let's consider some insights that might help in an interview setting. This problem is an excellent opportunity to showcase your mastery of the union find data structure. Be prepared to explain how path compression and union by rank optimize the operations and why these techniques are important. Emphasize the need for minimizing lexicographical order, as this is a critical requirement for producing the correct output. You should also be comfortable describing the graph representation of character equivalence relationships and how union find efficiently processes connected components. When discussing your solution, highlight how you handle edge cases, such as empty inputs, disconnected graphs, or scenarios where no transformation is required. Additionally, it can be helpful to draw connections to related problems that use similar concepts. For instance, LeetCode 721, where accounts are grouped by shared email addresses, LeetCode 547, which counts connected components in an undirected graph, and LeetCode 839, which involves grouping similar strings, all rely on union find. Even LeetCode 200, a problem about counting islands, can be solved using union find. These examples show the versatility of the approach and help solidify your understanding. Finally, let's explore some alternative approaches and their trade-offs. The most efficient solution for this problem is implementing union find with path compression and rank. This method achieves near constant time complexity per operation, making it highly scalable for large datasets. However, you might also consider using breadth-first search, or BFS, to traverse the connected components. While easier to implement, BFS is less efficient for dense graphs, with a time complexity of O(n squared). Another option is to use an adjacency list to represent equivalence relationships and perform a depth-first or breadth-first search. While functional, this approach is generally slower than union find. When evaluating trade-offs, consider the problem size and complexity. Union find is faster and more scalable, making it ideal for large inputs. On the other hand, BFS or DFS might be more intuitive for smaller problems, or when you want to demonstrate graph traversal techniques during an interview. Additionally, keep in mind the difference between optimized union find and its naive version. While optimizations like path compression and rank can add complexity to your implementation, they significantly improve performance for larger datasets, making them worth the effort in most cases. Thank you for following along as we solved problem number 1061, lexicographically smallest equivalent string. In summary, we applied union find to manage equivalence relationships and transform strings efficiently. Key takeaways include the importance of union find for equivalence problems and understanding lexicographical ordering. If you enjoyed this, please like, share, and subscribe for more coding content. Happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!